Okay, our last two problems from Chapter 3 on pumps and horsepower. Let's go ahead and take a look at these. So let's take a look at this problem first, similar to problem number 9 in Chapter 3 of the workbook. And it's asking you to calculate pump. Oops, excuse me. Let me make this a little bigger. Pump efficiency. And we know from previous problems that the pump efficiency is given as a percentage, like say 85%, 90%, and so on. So what we're really trying to determine is what percentage of motor horsepower, 25.2, is water horsepower, 21. And that is going to tell us what the pump efficiency is, right? Remember, we have to apply more horsepower to the pump to supply this amount of horsepower. We have to apply 25.2 horsepower to the motor to get 21 horsepower of force applied to the water. So how do we set this problem up? And I could just real quickly say, oh, it's easy. All you do is divide 21 by 25.2, and that is how you solve it. But I want to explain why that is. So we've been talking a lot about how the word per in math means that you have a division problem. So in addition to that, the word of is always going to mean multiply. So another way to think of this problem is if I want to know an unknown, and in this case I want to know that 21 horsepower is an unknown percentage, or we'll use X, of 25.2, right? 21 horsepower is what percentage of 25.2 horsepower? So I can rewrite this like so. 21 horsepower equals X of 25.2, or remember we said that X always means multiply. I probably should have used a different variable. So of means multiply. So 21 horsepower. Okay, let's just use a different variable so we don't confuse anything. We'll call it P. 21 horsepower equals P percentage of 25.2. We can rewrite this as 21 horsepower equals P, and of means multiply, so P times 25.2. Well, now that we've rewritten this equation this way, how can we get P on one side of the equal sign by itself? And hopefully by now it's pretty evident that all we need to do is divide both sides of the equation by 25.2. So it winds up looking like this. 21 horsepower divided by 25.2 equals P times 25.2 divided by 25.2. And then, because these are the same in the numerator and the denominator, we can cancel those out, and we wind up with P equals 21 over 25.2. At that point, we just do the division problem. 21 divided by 25.2 equals 0.833. And remember, percentages are expressed as decimals. So we can rewrite this as 83.3%. So that's how to do that problem. And then finally, our last problem here in the pumping portion of the homework is this one. And it is asking us to calculate the hourly cost for power to run this motor. And what information are we given? We're given that it requires 14 horsepower, and then we're given the price for electricity in kilowatts per hour. So how do we convert 14 horsepower into kilowatts per hour? First, we need to convert horsepower into kilowatts. And on your conversion sheet, or on your sheet given by ABC, there is a conversion factor right here, almost to the very last page. One horsepower equals 0.746 kilowatts, or 746 watts, or 33,000 foot-pounds per minute, but we're going to use the simple one. We just need to convert it to kilowatts. So right there, 1 horsepower equals 0.746 kilowatts. Let's write that down. 1 horsepower equals 0.746 kilowatts. So if 1 horsepower equals 0.746 kilowatts, then we should be able to determine how many kilowatts we need by multiplying 14 horsepower times 0.746 kilowatts is going to tell us how many we need. 14 times 0.746 equals 10.44. So again, if we wanted to write this out the long way to practice canceling out like units, we could write it like this: 14 horsepower over 1, and 1, or excuse me, 0.746 kilowatts per 1 horsepower. And then of course our units would cancel out, and we wind up with an equation that looks like this. So we know how many kilowatts we need. 10.44 kilowatts. Now we're also given the price of electricity in kilowatts per hour right here. So if we know it takes 10.44 kilowatts And the price of electricity is $0.031 per kilowatt hour. And we're only running the pump, or we're only calculating how much it costs per hour, so we don't need to factor in any time there. Then it just becomes one more multiplication problem. 10.44 times $0.031 or 3.1 cents gives us a final cost of 32 cents. So that's how to do that problem. You need to remember that 1 horsepower equals 0.746 kilowatts. Of course, a kilowatt in the metric system equals 1,000 watts. This conversion is also given as 1 horsepower equals 746 watts. So it is on the formula sheet. It's one of those numbers maybe that might stick in your head. When I took the Class 2 exam, I had trouble with these problems, and I practiced them enough that this conversion stuck in my head. And when I saw the problem on a test, I was able to kind of almost logically think my way through the problem by remembering that number. So it is on the conversion sheet. Make sure you know where all those conversions are on that conversion page, and that's how you solve that one. All right.